Okay, so let's have a look at week 10, problem 10.39. We have a steam power plant operating on the ideal reheat Rankine cycle between pressure limits of 15 megapascals and 10 kilopascals, right? So that's going to be our upper limit and our lower limit in the pressure scale. Reheat, so that we're going to have two turbines. And ideal, which is to say that our isentropic efficiency is 100%, right? So the mass flow rate of steam through the cycle is 12 kilograms per second. And steam entered both stages of the turbine at 500, right? So as I said, there's two turbines. Right? Both stages of the turbine, it enters the same temperature at 500 C. If the moisture content of the steam at the exit of the lower pressure turbine is not to exceed 5%, okay, so what is it telling us? What is this saying? That on there's two turbines. The one in which the exit has the lower pressure, this one cannot exceed 5% moisture, right? So this is actually telling us the quality, right? So if it's 5% moisture, it's 5% water, liquid, right? So therefore my quality is 95%, right? If 5% is liquid, then 95% is vapor. So under these conditions, determine the pressure at which the reheating takes place, the total rate of heat input to the boiler, and the thermal efficiency of the cycle. Okay, so let's have a look at a normal, let's say, a simple Rankine cycle. Okay, so we have a TS diagram here in the corner, and then we would go 1, 2, 3, 4. But in this case here, we have a reheat taking place, right? So our 4 is not going to be here. Instead, what we're going to have is we're going to go drop here at some point that we don't really know. That's going to be our 4. And we're going to have reheat taking place, and the reheat's going to go all the way into the same temperature as 3. So that's going to be our 5 there. And we're going to drop all the way down, and this is going to be our 6 here. Okay, so this is closer to what we have at the moment. Now, it says that the lower pressure one, the exit of the lower pressure turbine. Now, you'll notice that there's a higher pressure here, which is the high pressure on this guy here. So this pressure here is all the same pressure, and that's 15 megapascals, right? So this guy is 15 megapascals. And then we have the lower end here, which is this guy here, 10 kilopascals. So 4, 5, these two guys, they are the mid-range one. So the exit of the low pressure turbine will be the exit 6, right? There's two exits of the turbine. There's 6 and there is this right away. So there's 6 and there's 4, right? We have 6 and 4. And then between the two, 6 has the lower pressure. So this guy here, this state here, the moisture content can be maximum have 5% moisture. Okay, so at this point here, at point 6, we have a 95% quality. All right, so I've written down the properties that we know already. We know pressure 1 equals pressure 6. That's the low end, 10 kilopascals. 2 and 3, that's the high end, 15 kilopascals. And T3 and T5 are both 500 C. We also have the mass flow rate that we will be using on this part here, right? Because if you notice, this guy here is in kilowatts, so we're going to be needing that mass flow rate there. Okay, so how are we going to solve this cycle? Let me actually get rid of these green guys here. Right, how are we solving this cycle? Well, this cycle, we have information for 1, that's easy, then we can use that to find 2, that's easy. 3 is pretty much defined, it's easy. Okay, but then for 4, we only know we're only going to be able to find the entropy from here to here. So we're only going to have one property for 4. So we can't really solve it from there. And for 5, same thing, we only have the temperature and nothing else. Okay, but 5 and 6 have the same entropy, right? If they have the same entropy, we can define 6 first to find properties of 5, and then from 5 find things for 4. So that's going to be the way we're going to take to solve this guy. All right, so the beginning is like before, nothing new. So let's go ahead and do that. Just like we've been using lately, right? For my state 1, I know it's a saturated liquid, so I'm going to go on table A5 because we have the pressure, right? So we're going to look at the pressure table on table A5, and I can go ahead and grab the enthalpy for the saturated liquid, and I can go ahead and grab the specific volume for the saturated liquid, which I'm going to use to calculate state 2. Right, so state 1 has been defined. I have the enthalpy nice and neat here from the start, and that's easy. Then state 2, we're going to apply the same as before as well. We have the work that we need to put into the pump, the energy of the pump or the energy of the compressor, right? So that's why you have P or C there, is the difference from the enthalpy state 2 and state 1, which is approximately equal to the specific volume of 1 times delta P, again, because this fluid is incompressible, right? Water is incompressible fluid if we have it in the liquid form. So this V is pretty much not going to change. So that's why we can do this approximation over here and make our lives easier. Only thing to remember is that, so therefore I can find my H2 straight off the bat, just summing up H1 plus the difference in pressure times the volume. The only thing I need to be aware here is that when I'm doing this sum here, these guys obviously have to be in the same units, right? So I need to ensure that this multiplication here is coming out as kilojoules per kilogram, right? And to do that, I'm going to need this guy here in kilopascals. That's why I converted the megapascals into kilopascals. And this guy here in meters cubed per kilogram, which multiplied is going to give me kilojoules per kilogram. And so I've defined state 2 as well. I got state 2 to be 206.9. And then I can jump into state 3. In state 3, I have two set of properties, right? I know P3 and I know T3. So if I've got it completely defined, and I'm going to jump into the table, I'm going to note, you can use pressure table or temperature table, whatever you find easier. And in this case, I use the temperature table because I looked at 15 megapascals and I saw my temperature T3, that is 500, is greater than my Tsat. So I can conclude this guy is a superheated fluid. So instead of looking on this table, I'll be looking on table A6, right? So I'm looking on the table A6. And since I have pressure and temperature, I can go ahead and grab enthalpy. I can go ahead and grab entropy. Why am I needing entropy? Because if you guys recall, the entropy on state 4 and 3 are the same. So if I can grab this guy here, I can define my state 4, at least half of it, right? So that's precisely what I do. Jump into state 4. And then on state 4, I know that the pressure of 5 and 4 are the same, and the entropy of 3 and 4 are the same. Okay, so this guy is done, and I have this, but I don't know the pressure yet, so I can't really do anything on 4 at this moment. Okay, so I'm going to leave like so for now. I'm going to jump into state 5, and kind of the same thing happens, because on state 5, we do have the temperature, that's fine, but we don't know anything else. The other thing that we know from the diagram is that the entropy on 5 and 6 are the same, but I don't know the entropy on 6 yet. So what do I need to do? Again, skip this state and go straight into state 6, so that when I figure out things from state 6, I can go ahead and go back here and then continue solving. Okay, so let's find things for state 6. Now, state 6, I have two information. That's all I need to define the state, right? I know that the pressure is 10 kilopascals, like it's the lower limit, and I also know the quality because it's been said that on the exit of the low pressure turbine, my moisture cannot exceed 5%. Therefore, my quality is 95%, and because I have a quality, because I have this mixture, this state is a saturated mixture, right? If it's a saturated mixture, then we know all the properties are going to be a mixture as well. Right, so entropy, enthalpy, specific volume, and so forth, they're all going to be a combination of the liquid and the vapor according to how much we have of each. So what I do now is I go straight onto table A5, 10 kilopascals, and off this table I can read all the information that I need, right? So I can read the saturated liquid entropy and the saturated vapor entropy. I know the quality rate, it's 95%, and this is going to be my 5%, right? So I can rewrite this equation with the values that I can grab from the table, and I can find what is the entropy for state 6. Okay, so once I find this guy here, once I find this entropy for state 6, this is what I need to be able to solve for my state 5, right? So let's just put that down. So that's going to be 7.7738. So 7.7738 kilograms Kelvin. Okay, so now I have two things for state 5 and I can solve this guy. But since we're doing this already on state 6, let's just finish off and grab the entropy, right? It's going to be exactly the same idea of the entropy, but instead of putting entropy values, I'm going to be putting entropy values here and here. And I can solve for that guy and grab my entropy for state 6. Okay, so now I have state 1, 2, 3, and 6 defined. I'm missing 5 and 4. So let's go back and let's do 5. Okay, so now I have two things for 5, which means that I can now define 5 completely. What I did is I went straight into my table and I was looking at the temperature table for 500. So I'm looking at, because I know T is 500, I can look at the temperature table, and you can look at the entropy for the vapor at the temperature table, and you'll see that our S, which is 7.7738, is greater than the vapor one. So that means it cannot be a mixture, it cannot be saturated vapor, it has to be a superheated state. Okay, so if it's superheated state, we can look on table A6. Now there's one tricky thing here, which is that you note that our entropy falls between these two guys here, 7.86 and 7.77. This guy here is on one page, 0.8 megapascals, and this one's the next page, 1 megapascal. Okay, so that means that our pressure for state 5 has to fall somewhere between 0.8 megapascals and 1 megapascal. Okay, so what I'm going to do, I'm going to interpolate with the value that I do have. That's the S5 that we just grabbed by solving state 6. And interpolating that for the pressure, I get 0.98. So that's about 982 kilopascals, right? So pressure 5 is about 980 kilopascals. And this is precisely what I need to be able to solve for state 4, right? Because I know these pressures are going to be the same. This is also useful because, actually not useful, but this is what part A is asking us, right? What is the pressure at which reheat takes place? Reheat is from 4 to 5, so that's going to be 980. So that's going to be 980. Okay, then I can, now that I know my state 5 completely, okay, then now that I know my state 5 completely, I can go ahead and find the entropy the same way, right? Now I know, well, there's two ways you can do it. You can actually have another, let's do it here. Let's just get rid of this. The other thing you can do here, if you want to save yourself some time, is you can just put another column here, if entropy, put the values for entropy for this guy and for this guy, and just interpolate once more. I actually did it again, right? So I did the same thing, interpolation, and then interpolated for the 0.98, and I got the entropy for this state. Yeah, it's superheated, so there's only one value for entropy. You just need to interpolate between the two states. Okay, so I have state 5 completely defined, and now that I just found the pressure, I can go back to state 4. So let's go back to state 4. Where's my state 4? Yeah. So now we have two things, right? We have the entropy from state 3, that's the 6.34 over here, and we have the pressure from state 5, which is the 980 kilopascals. Okay, so now that I have two things, I can solve the state, right? I have everything that I need for the state. Now this is the one that takes, it's the, how can I say this? Well, it takes the most effort from you guys because it's just a dough process. You see, let's just follow this green arrow here. Okay. Now the problem is, as you'll notice, our pressure table doesn't have a 980 value. Okay, we have a 950 kilopascals and we have 1,000 kilopascals. So you're going to have to do heaps of interpolation to be able to find out what's happening. Okay, so what I'm doing is I'm finding the entropy for saturated liquid and vapor, because what I do have is the entropy for state 4, right? And to be able to define whether this is mixture, superheated, saturated, I need to find these entropies here. So you're going to do interpolations to find what's the saturated vapor at 980, saturated liquid at 980. And then because we were after enthalpy, I went ahead and also did all at once when I was solving it, the enthalpy for vapor and the enthalpy for liquid as well. Okay, you could do this in 2 steps, but since I knew I was going to have, I was after enthalpy, I just did it all at once. Okay, so you're going to grab values for all of these guys just by the interpolations. And what we can do is now we can define the state. Okay, let's just first start here. Okay, so I found by interpolation, I found that the entropy for the saturated vapor at 980 is about 5.59, and the saturated liquid is about 2.12. Our value is 6.34 something. Okay, so therefore that means that that's quite easy to see here, that my value falls between these two guys here, right? It's small in this guy and greater in this guy. So that means it's a saturated mixture, right? Actually, I wrote this down here. Because my S4 falls between my S liquid and my S vapor, it's a saturated mixture, okay? And I'm actually highlighting this is not superheated, okay? So what that means is, before we move forward and calculate the enthalpy, let's go back to our diagram. Where's my diagram? Here it is, okay? So that means that this drawing is incorrect, right? Because you can notice, if you notice, this drawing is showing 4 over here, which would be superheated. Okay, so if I were to draw this correctly, if I needed to draw the PV diagram, or DTS diagram, I should say, I would drop from 3, I would drop here at some point, right, saturated mixture. Then I would reheat at constant pressure until I reach my 500 over here. And then I drop again all the way to 6, which is also a mixture, right? 95% vapor, 95% liquid. Okay, so my 4 will be down here instead of where we drew it originally. That's what we just found out. Okay, so let's finish off state 4 and find the enthalpy for it. Okay, if it's a mixture, we know the enthalpy is going to be a combination of both saturated liquid and vapor. Okay, we know it's going to be an equation like so, and we just grab this guy off the interpolation. We grab this guy off the interpolation as well for 980, and then the quality we don't have, but since we have entropy, we can use that, right? So we have the value for entropy, we have S liquid, we have S vapor, S liquid, so I got the quality to be 94.53%. Okay, so once you have that value, you can plug that guy in there, and in there, and we can solve for enthalpy, and I got approximately 2,666 kilojoules per kilogram. Okay, so now at this point, what we found out is that we have, we finished the whole system, right? So now we define the whole system. Check it out. Let's have a look at what we have. We have the enthalpy for the first state, completely defined, enthalpy for the second state, enthalpy for the third state, and this guy took us a while, enthalpy for the fourth state. We also grab the enthalpy for this fifth state over here, and we have the enthalpy for the sixth state over here. Okay, so they're all defined. So now solving part B and C are quite easy. Part B is asking us how much, what total rate of heat input to the boiler. Now, if we're looking at this, let me grab the blue. So if we're looking at this, where are we inputting heat to this cycle? Well, we're inputting heat from 2 to 3 and also from 4 to 5, right? That's why it's a reheat system. We have 2. So we have 2 boilers there, and we have 2 stages at which we input heat. So if you want to find the total amount of heat, we're going to have to do from 2 to 3 and from 4 to 5. Okay, and once we find that, then to find the thermal efficiency, we just find the Q out, and there's only one Q out from 6 to 1. That's where our Q out is. So we can find that guy and finish off. Okay, so we just need to use all the enthalpies we just found. That's easy, right? Once we have the enthalpies. Alright, so Q in, like I said, is relating from 4 to 5 and from 2 to 3. and I got 3,900 kilojoules per kilogram. But as you guys recall, they want the answer in kilowatts, so we have the mass flow rate, just multiply one by the other, and I got 47,000 kilowatts, right? So about 47 megawatts. And then again, we have two options. From here, we can, to find the thermal efficiency, we can either find Q out or we can find the work. But since we need Q out to find the work, now it's probably easier to just find Q out and just do that. So my Q out is from 6 to 1. Let's do like this. From 6 to 1, so just 6 minus 1, I got, so this is 6, this is 1. So 2,200 kilojoules per kilogram. Okay. So we can use the thermal efficiency by relating the two heat, right? Heat addition and heat rejection. The only thing that you need to watch out is that because you need to eliminate the units on this guy here, right? Because this is dimensionless. You need to make sure you can't use the 47, right? It may be tempting to use 47 as Q in there, but in that case we would have, let me highlight this over here again. So you'd have kilojoules per kilogram divided by kilowatts. So you would not eliminate your units. So you must use the 3,900 because this is also in kilojoules per kilogram. Right, so Q out is a 2272, Q in is 3917, and with that we get an efficiency of about 42%. Yeah, 41.89 or so. No, 41.987% is what I got. Alright, hit me up if you have questions. If not, I'll see you guys soon.